Okay, Assalamualaikum and good morning, everyone.
Waalaikumsalam, Dada.
Waalaikumsalam, Dr. Good morning.
Morning, sir.
Okay, thank you. All right, so today we will continue with our lectures. So, uh, on Monday, we have learned about how to use Laplace transform, partial fraction expansion, and inverse Laplace transform. And today we will look at how we can derive transfer function, which is we have learned on Monday. How what is a transfer function, and today we will learn how to derive transfer function from a translational mechanical system. So a translational mechanical system is a system that involves motion either horizontally or vertically without involving any rotation. Okay, so after completing this lecture, you will be able to create transfer function for translational mechanical system, for single degree of freedom, and multiple degree of freedom system. Okay, so before we go into learning about how to derive the transfer function for translational mechanical system, let's look at the motivation or the reasons why we need to have the transfer function. So let's say we have this plate dispenser. So I'm not sure whether in what kind of restaurant that use this dispenser. So what happens if we remove the top plate? How to model this system? So whenever so the spring will have less load, and because of less load, then the spring will extend, okay, causing the platform to rise up, and the next plate will be on the top. Okay, so you can just take the plate until all of the plate is removed. So we can make a similarity from this system into a mass spring damper system. So we have a mass here. So the mass maybe consists of the piston surface, and we have a force. So the force represents the plate that is put on the piston, and then the piston has a spring, and the damper maybe represents the friction between the piston and the surface of the dispenser. So we want them to measure the displacement of this piston or the mass. So we can label the position of the mass as y. Okay, so the force as F. So we can derive the transfer function for this system. So the basic things that we want to do is to control the position y given a force F. Okay, so how we can control y given a force F? Okay, so actually we want to derive this transfer function of this system. So let's look at how we can derive this in a more general way. So let's say we have a single degree of freedom system. So a single degree of freedom system has a mass and probably has a damper, a spring, and also a friction. So the spring has a constant K, the damper has a constant FV1, and then the friction has a constant FV2. So we have a force F, and we want to measure the displacement of the box of the mass M. So we label the displacement as X. So we would like to model the motion of the mass M. Okay. So firstly, what is degree of freedom? So this is a single degree of freedom system. So what is degree of freedom? So degree of freedom is basically the number of unconstrained motion. So how many unconstrained motion can we find from this system. So unconstant motion means that the motion that allow the box to move. Okay, so this box can move either forward or backward. Okay, horizontally. So let's say if we fix the spring and damper, so the box cannot move. Okay, or if we meaning that we only fix one thing, meaning we fix the box, then everything cannot move. So here there is only one thing that is able to move, which is the box either forward or backward. So this system is a single degree of freedom. So later we will see a 2 degree of freedom system and multiple degree of freedom system, and we will see how we can identify the number of degree of freedom for the system. So to model the transfer function of this system, there are 4 modeling steps. So firstly, we need to decide what is the input and the output of the system. And then we need to list all the forces acting on the mass by drawing the free body diagram. And then we convert the force into frequency domain using Laplace transform. And then lastly, we isolate the output from input to get the transfer function. Okay, so this modeling steps are the general steps, okay, which will be applied for all uh, mechanical system that we want to find the transfer function. So let's look at how we can derive the transfer function using these steps. Okay, so step 1 is to decide the input and output. So this is the figure for the single degree of freedom just now. So the input is the force. Okay, so when we apply the force, then the mass will move. Okay, so if we don't apply any force, which is the input, then the mass will stay, it doesn't move. So input is the force, then the output is the motion, which is the x. So we can also from x we can also find the velocity, which is x dot, and also we can find the acceleration, x double dot. So the output can either be position, velocity, or acceleration, depending on what you want. Okay, so most of the time we want position, but maybe we want to find velocity or acceleration. And then after we identify the input and output, then we can list all the forces on the system by drawing the free body diagram. Okay, so from this system, we have force from the spring, the internal force. Okay, so we have the force from spring, from the damper, from the friction, and we have the inertia of the body because it has a mass, and we have the input force. So all of this force can be uh, shown by drawing the free body diagram. So the figure on the right here is the free body diagram. So we have input force, which in this figure is acting forward, and all of the other force like spring, damper, friction, and the inertia will be acting backward. So why all of these forces are acting backward? Because you have to imagine that when we apply the input force forward, so all of the forces like spring, damper, friction, and inertia will try to resist the force applied. Okay, so we'll try to resist the input force such that it doesn't allow the mass to move. Okay, so all of the forces from spring, damper, inertia, and also friction will be acting backward, okay, against the input force. Okay, so that's why all of these are acting backward. Okay, so there are 5 forces, including the input force. And if you have mass, like for example, this box has a mass M. So don't forget the inertial force, which is M x double dot. Okay, so from damper and friction, it's the friction or the coefficient FV1 or FV2 multiplied by the x dot, okay, the velocity, and the spring constant times the displacement x. And for inertia, it's m times x double dot, or the acceleration. So here is the conversion table for each of the forces. So spring just now, it's k times x, k time displacement. So in time domain, it's k times x. So to convert into frequency domain, we use Laplace transform. So it becomes k times xs, okay? Or just k. Can also write k times xs. And then for damper or friction, so damper and friction has the same um, force equation, okay? So for damper or friction, it's Fv times x dot, or the velocity. So in frequency domain, it becomes Fv times s xs. And lastly, for the inertia, for the mass, m times x double dot, or acceleration. So in frequency domain, it becomes m s square times x s. Okay, so I hope you can remember this. So for spring, it's just kx. For damper, it's Fv times x dot. For mass, it's m times x double dot. It is similar for every cases, okay? So I hope you can remember this. Then after we convert into frequency domain, then we can um, write the equation of motions. Okay, so this is the free body diagram from previous slide. So we convert all the forces using Laplace transform. So kx become kxs, fv1 x dot becomes fv1 s xs, mx double dot becomes ms square xs, and fv2 x dot becomes fv2 s xs. So xt becomes xs, and ft becomes f of s. Okay. Then we can write the equation of motion. So we just write the force balance. So force acting backward equals force acting forward. So the left hand side here are the total forces acting backward equals the forces acting forward, which is F. And then we can factorize XS. So after factorize, we can find the transfer function. So let's say if you want to find the position, the output position, so you can write the transfer function. Let's say gs equals xs over fs equals. So you just factorize xs and rearrange the equation to get this transfer function. And if you interested in to find the velocity, so you want to find x dot or sxs, so the transfer function becomes x times s over f and you just rearrange the equation to get the transfer function. And similarly, if you want to find acceleration, so you want to find x s squared, so you just calculate the transfer function x s squared over f equals 1 over the equation. Okay, so you just rearrange. Okay, any questions so far?
No, sir.
Okay, let's go back to the restaurant dispenser. Okay, so the restaurant dispenser is an example of a single degree of freedom system. Okay, so it has damper, spring, inertia, or the mass, and then input force and the displacement. So we want to find the relationship between yt and ft, or the transfer function. Okay, so you can derive this using uh, the example that I explained just now. So uh, so here the example given to you here doesn't draw the free body diagram. So later you can draw by yourself. Okay. So in the figure, there are three forces that tries to resist the motion uh, by the input force F. So we have Fv, the damper, we have spring, and also the mass M. So we can write the equation of motion. So K times X, or K times Y, plus FVS. So FV times YS, or FV times velocity, plus M times uh, acceleration, Y double dot. In frequency domain, it becomes ms squared. Okay, equals F. So forces acting backward equals forces acting forward. So in this case, F is acting backward. So the forces from damper, spring, and the inertia will be acting forward because it tries to make sure the mass will not move. So the force is acting downward. So the other forces like damper and spring will push the box upward. Okay. So rearrange this equation to get transfer function of y over f equals 1 over k plus fvs plus ms squared. So let's say you are given these values: k equals 2 Newton per meter, fv equals 3 Newton second per meter, and m is 1 kg. And then the force F equals 2 Newton. In frequency domain, it becomes 2 over s. Okay. So you just convert using Laplace transform, you get 2 over s. So you just substitute all of this into the transfer function g. So you substitute everything, you get this transfer function, and then f equals 2, 2 over s. So just rearrange, and then you get y equals this equation. So from here, you can apply the partial fraction expansion that we have learned on Monday. So here is an example how to apply the partial fraction expansion. So a over s, b over s plus 2, c over s plus 1. So you find the value of a, b, c. So you find the value of a, b, c, and then substitute back into the ys. So you get ys, then you apply inverse Laplace transform. So you get yt. So this is the things that we want. Okay. If you do control system, okay, we want the time response of the things that we want to measure. Okay. So in this case, we want to measure the position of the piston. So when we get the time response of the position, then we can plot the graph. Okay, so from the graph here, we can see that the position YT is actually increasing, okay, but I tak tahu kenapa dia negatif. Okay, whatever. It's actually increasing until a certain time, about 8 seconds. Then the position will become constant. Okay. So here, meaning that when we take the plate, okay, when we take the plate, which is the force is 2 Newton, then the position will increase. It takes 8 seconds before it can reach a constant value at the top. Okay. So in control system, actually what we want to do is we want to make sure the time taken here to reach the steady state value or value -1 here is as fast as possible. This 8 seconds is actually fast already, but sometimes we want to design a controller that make this time a lot faster, maybe 4 seconds or 2 seconds or even 0. Okay. But ideally, we want it to be 0, something like this. But in real life, we cannot get this kind of time response because there will be some damping, okay, occurred in the system. We cannot remove the damping or vibration. So the best we can get is maybe 4 or 2, which we will learn later. Okay, maybe after midterm. What happened if we try to increase or reduce the time taken to reach the steady state value? Okay, so that's the idea of how we can apply derivation of trans function until finding the time response using partial fraction expansion. So now let's look at an example of multiple degree of freedom system. So just now we have learned a degree of freedom system. Okay, so the same modeling step we will use in this multiple degree of freedom system. So firstly, we need to decide the input and output from the system. What is the input and what is the output that we want? And then we can list all the forces by drawing the free body diagram. And then we can convert the forces into frequency domain. And lastly, we find the transfer function by isolating the output from input. But now we have two boxes. Okay. So in this example, we have two boxes, meaning that we have 2 degrees of freedom. Because here, from the figure, we can see that we have two displacement, x1 and x2. So we have x1 measuring the displacement for box M1 and x2 measuring the displacement for box M2. So we have 2 degrees of freedom, or we can determine the degree of freedom by assuming, for example, we hold this box M2. Let's say we hold this box so that M2 is fixed and not move. Then we can see that only M1 can move either backward or forward. So we have 1 degree of freedom here. And then we fix M1. Okay, so we fix M1. And then we can see that only M2 can move either backward or forward. So here we have another degree of freedom by M2. Okay, so there are 2 degrees of freedom in this system. So when we have 2 degrees of freedom, meaning that we have two free body diagram that we need to draw. Okay, so let's look at how we can draw the free body diagram. Okay, firstly, we need to decide the input and output for the system. So the input is usually or always be the force. Okay, so here the force Ft is applied on M2. So when we pull M2, M1 will also move. It can be x2 or x1. Okay. But in this example, we use x2 as the output. Okay, just to show you how to get the transfer function.
Doktor,
Hmm.
slide tak ada pun. Slide hilang. Ke saya seorang je?
Ada.
Ada. Sekejap, saya share balik. Ada tak?
Ada.
Okay, tadi internet saya down sekejap. Okay, so let's look at how to draw the free body diagram. So free body diagram. So kena lukis sendiri. Okay, so we have two mass M1 and M2. So let's look at the first mass first. Okay, the M1. Okay, so M1, we have three forces or four forces acting on the body. Okay, so first is the spring K, K1. Second is the damper FV1. And then the third one is the spring K2. Okay, so to determine the internal forces on the body, we look at how many elements that are connected on the box. Okay, so in this case, for M1, we have K1, FV1, and also K2. And on M1, we don't have any input force because input force is applied on M2. Okay, so alah, tak ada gambar. So let's draw. Have identified three elements, and because the box has a mass M1, then we need to consider the inertia as well. Okay, so I draw the free body diagram number 1 first. Okay, so the forces from the spring and damper and also the inertia will try to resist the motion of M1. Okay, so M1 is moving forward, okay, because of this sign here, X1. So X1, the direction of X1 is going forward. So the forces from K1, FV1, and K2 will be backward because they try to resist the motion of M1 from going forward. So we have K1X1. Okay, we have force from spring K1, so K1X1. And then we have the force from damper. Okay, so FV1 times X1 dot, the velocity. And then we have the forces from spring K2. So we have K2 X1. And also we have the inertia from the mass. Okay, so we have the mass M1 X1 double dot. Okay, so M1 times the acceleration X1 double dot. And then if you notice that this spring K2 is also attached to M2. Okay, it doesn't attach to M1 only, it's also attached to M2. So we need to consider the force from the spring K2 by the box M2, because it's applied, it is connected to both of the box. If you look at the spring K1 and the damper FB1, it is connected to the wall. Okay, so the wall is fixed and not moving. So the force from the wall can be assumed zero. Okay, but now K2 is connected to M1 and also M2, but M2 is moving. Okay, so we need to consider the force from M2 by spring K2, meaning that we need to add a force K2 X2, okay, somewhere in the free body diagram M1. So usually we can add straight away here, because this is also K2. So you can add, instead of writing like this, you can add K2 X1 minus X2, replacing this force here. Okay. But what I did usually, I split this force into two. So what I did usually is I put a backward force or backward arrow. I write K2 X1. Okay, so K2 X1 is always acting backward. And then I add a forward arrow. And then the force is K2 X2. Okay. You can write K2 times X1 minus X2, but the direction is backward. Or you can split the force K2 X1 backward, K2 X2 forward. So the reason why I split the force, because later when you want to write the equation of motion, it's a lot easier, because in the end you need to split them anyway when you want to write the equation of motion. But both of the answer is acceptable. Okay, is correct. So if you write K2 times X1 minus X2, but the direction is backward, is correct. Or if you write K2 X1 direction backward and K2 X2 direction forward, you split the forces, also correct. Okay, so whichever whichever way you write is okay. So when you have an element, let's say spring, connected on two body, then the force becomes x1 minus x2. Okay. Any question, just ask. Okay. So now let's draw the free body diagram for M2. So on M2 we have spring K2, only one element. Okay, only one element, spring K2. And on M2 we have also the inertia, and we have the input force Ft. So let's draw the free body diagram of M2. Okay, so we can start by drawing the force. Okay, and then the forces from the elements that are connected to M2, like the spring, will try to resist the motion. Okay, so the motion of M2 is going forward. So the forces from spring and also the inertia will try to resist the motion of the box from going forward. So we have one backward force, K2 X2, and then another force. Okay, saya tak boleh lukis dekat diagram ni sebab sempit. Okay, jangan salah faham pula. Okay, so we have another force from the inertia. So we have M2 X2 double dot. And then the K2 the spring K2 is also connected with M1. So we need to consider the force from M1. Okay. So similar to free body diagram number 1, you can write x2 minus x1. Okay, you can write here x2 minus x1. Or you can split the force. Okay, you can write one force going backward k2 x2, or uh, you can write one force going backward k2 x2, or k plus k2 x1 going forward, or you can write in this form k2 times x2 minus x1 and the force going backward. Okay, so I hope you understand. Later you can do by yourself. Okay. So when you draw the free body diagram, then you can write the equation of motion. Okay, so this is the first equation of motion from free body diagram M1. And then the second equation is equation of motion for free body diagram number 2. Then when you have two equations here, usually you will have to write in matrix form. So you have to write this equation in matrix form because we want to solve this simultaneously. You can also write. You can also solve this manually, simultaneously without writing in matrix form. But writing in matrix form is easier. Okay. Later we will use a technique on how to solve this equation. So rearrange the equation into matrix form. Okay, so this is in the matrix form. Then if you want to find x1 and x2, you can just use the matrix without solving this manually. Okay, so here we use a theorem called Cramer's rule. So I think you have learned Cramer's rule maybe in numerical method code and also finite element method. I'm not sure. So we can use Cramer's rule to find x1 and x2. So for example, if you want to find x1, so x1 equals, so this is the determinant. Okay, ada silap kat sini. So determinant of matrix. Okay, so I hope you understand what is determinant of matrix. So to find the determinant, to find x1, firstly on the numerical and on the numerator, you find the determinant of this matrix. So how to get this matrix? You have to substitute the first column of the big matrix here by the force matrix, or the by this column. Okay, so substitute this column by this column 0 and f, and then the second column you remain it as usual without substituting anything. So find the determinant divided by the determinant of this big matrix. You find the determinant of the big matrix, but substitute the second column. Okay, second column with 0 and f divided by the determinant of the original big matrix. So x1, you substitute 0 and f into first column, but to find x2, you substitute 0 and f into the second column. So 2 by 2 matrix, I think you can calculate the determinant manually by hand. Okay, but for 3 by 3 later, susah sikit. So this is how you find x1 and x2. Okay, any question regarding this multiple degree of freedom?
Tak ada lagi doktor. Okay, kena cuba dulu untuk yang ni kan. Grammar tu. Baru saya nampak.
Betul. Okay, so apa dah? Okay, 10. Okay, I think that's it for now. So you can explore tutorial first. Tutorial 3. Let's see what's tutorial 3. Okay, so maybe you can try tutorial number 3, question number 1A. So 1A is a 2 degree of freedom system, and 1B is a 3 degree of freedom system. So maybe you can try question 1A and then 1B. Then we will discuss next week, insyaAllah Monday. Ada banyak lagi. Okay, so that's it for today's class. Any question?
Tak ada doktor. Saya cuba buat yang tutorial.
Okay, so that's it for today's class. Try your tutorial first. Then on Monday, we will discuss the tutorial and continue the rest of lecture number 3. Okay, that's all.
Okay,
Thank you very much. Assalamualaikum. Goodbye.
Thank you doktor.
Thank you, Doktor. Salam.
Thank you
Thank you.
Thank you, sir. Thank you, Doctor.
Thank